Polarity occurs because there's unequal sharing of electrons due to electronegativity difference. In the last unit, we learned that electronegativity increases going diagonally up to fluorine on the periodic table. When there's an electronegativity difference, a dipole moment is created. A dipole, there are two poles in which we have a center that is positive and a center that is negative. The one that is more electronegative will have a negative partial charge. The one that is least electronegative will have a positive partial charge. The symbol for dipole moment is delta negative for the more electronegative or the center of negative. The least electronegative will be delta positive. Or you could use an arrow. The tip of the arrow goes to the more electronegative. The tail of the arrow with a plus goes to the least electronegative. Another way to state it is the one with the delta negative will have more electrons or a higher density of electrons around it. The element with the least electronegative will have less electron or a lower density of electrons. Earlier in the year, we divided the types of bond into two categories, covalent bonds and ionic bonds. Ionic bonds were between a metal and a nonmetal. Covalent bonds were nonmetal and nonmetal. The covalent bonds are further divided into nonpolar and polar covalent. We determined the types of bond by using the following formula. The change in electronegativity is equal to the electronegativity of element 1 minus the electronegativity of element 2, taking the absolute value. Since we are taking the absolute value, it doesn't matter which one I subtract first. In general, the range for nonpolar covalent bonds is between 0 to less than equal to 0.4. For polar covalent is 0.4 and greater, but less than equal to 2. Anything greater than 2 is considered to be ionic bonds. However, if you have a metal and a nonmetal that falls into this range, when you do the electronegativity difference, it is not considered polar covalent, but it will fall under ionic bonds. On the test, you will be provided with the same electronegativity chart you received in class. The following are Lewis-Dot structure that you already did for homework or read these in class as we were completing the Vesper tables. Using your electronegativity chart, we're going to calculate the polarity of each bond and then the overall molecule's polarity. So using your electronegativity chart, we're going to find the polarity of the HS bond. General formula is delta En is equal to absolute value of En1 minus En2. Our delta En is going to be our En value of H minus En value of S. And again, it doesn't matter if you do the S minus H or H minus S because we're taking the absolute value. On your chart, H should be 2.1, S should be 2.5, so this is going to be 0.4 if I subtract it. This is going to be nonpolar covalent. The arrow is going to go towards the sulfur. There are two bonds. Both arrows are going to go towards the sulfur. However, when we do the delta En, it is always between two elements. We do not double or triple the elements if there's more than one element. We know that the individual bonds are nonpolar. However, the overall molecule is polar. The net dipole will go up here if I add it. So the red is the overall dipole moment of the molecule. Pink are the polarity or the dipole moment for each bond. So if I look at CO2, we have oxygen. So this is going to be En of oxygen minus En of carbon. Again, we just do each element. Oxygen is 3.5 minus carbon, which is 2.5. So this is equal to 1. So this is polar. Each bond is polar. So if I draw the polarity of each of the bond between C and O, they're going to go towards the O because the O is more electronegative. Since this structure is linear, the overall molecule, there is no polarity. There's no dipole moment for the overall molecule because the polarity cancel out from the bond. So the overall molecule is nonpolar. For H2S, the overall molecule is polar. If I look at CO3 2 minus, if I do the electronegativity, it's going to be the same thing as CO2. We know that the dipole for each of the bonds are going to go towards the oxygen. This is trigonoplanar. Trigonoplanar, it is going to be nonpolar for the overall molecule. Because in 3D space, the oxygens are pulling equally, and so their polarity cancels out. For NH3 delta En, this is going to be the En of hydrogen minus the En of nitrogen. Hydrogen is equal to 2.1. Nitrogen is equal to 3.0. So this is going to be 0.9. The bonds between hydrogen and nitrogen are polar. And the arrow is going to go towards nitrogen. This time I'm going to use the delta. So the least electronegative will get the positive delta. The more electronegative will get the negative delta. It will look something like this. You could use the arrows or the deltas. Since this is a tetrahedral trigonopyramidal, because there's 3 bonds, 1 lone, it adds up to 4. There is a dipole moment. The dipole moment is towards the nitrogen and the lone pair. The molecule is overall polar. The polarity or the dipole will go towards the nitrogen. CH3F, we have to calculate 2 bonds. We have to do the delta En between the hydrogen and carbon. Hydrogen is 2.1, carbon is 2.5, which is 0.4. That bond is considered nonpolar, even though it has a slight dipole moment, which is towards the carbon. So that's going to be delta positive. This is going to be a delta negative for this one. Same thing here. Now we have to calculate the polarity between C and F. So delta En is equal to En of the fluorine minus the En of the carbon, absolute value. So that's 4.0 minus 2.5, absolute is 1.5 is the difference. And so if we draw this here, the carbon is a delta positive and the fluorine is a delta negative. So the polarity overall molecule will be polar and it will go towards the fluorine. Now let's look at these structures, BrF2 minus. So here we have electronegativity difference between Br and F. F is 4, Br is 2.8. This is equal to 1.2. So this is, each bond is polar. And the polarity goes towards the fluorine. And so the bonds are polar. However, the overall molecule is nonpolar. And the reason the overall molecule is nonpolar, this is a linear trigonopyramidal. The bonded pairs form a line. They are in opposite directions. Even though each of the bonds have dipole moment, they cancel each other out because they're in opposite direction. The lone pairs are in a plane that makes an equilateral triangle. So the lone pairs here, 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 they repel equally, so they cancel out. So the overall molecule is nonpolar. IF5, we have an electronegativity difference between I and F. fluorine is 4.0, iodine is 2.5, so this is equal to 1.5. The bond between fluorine and iodine will be polar. Fluorine will get the delta negatives because it's higher electronegative, and the iodine will get the positive. So overall molecule will be polar and it will go towards the fluorine. The last one, we have a bond between Xe and delta En is equal to En of Xe minus En of F. Xe is equal to 2.6 minus 4.0. This is going to equal to 1.4. The individual bonds are polar and they're going to go towards the F. This is going to be delta negative, delta negative, delta negative, delta negative, and Xe is going to be a delta positive. So each of the bonds are polar. However, the overall molecule is non-polar. The fluorines are in a square, so they cancel each other out. This is a square planar. The fluorines are in all opposite ends and they are pulling each other equally. The lone pairs make a line, so we have a lone pair on top and a lone pair on the bottom end, so they cancel each other out. The overall molecule is nonpolar. So to determine the polarity of a molecule, we're talking about the overall molecule, you're going to look for symmetry. Symmetry means everything on the outside have to be exactly the same. And you look for lone pairs. Nonpolar molecules must have symmetry and no lone pairs. So when we are talking about symmetry, it has to be the same throughout. So for example, if I have HCH like this is not symmetrical. Because if I cut it this way, it is symmetrical. If I cut it horizontally, it is not symmetrical. The bottom one has H, the top one has an F. So symmetry means the outside elements are all the same. Second, no lone pairs. There are two exceptions to the rule. If it's symmetrical and is trigonal, bipyramidal, linear, and it is octahedral, square planar. These are also nonpolar. A trigonal bipyramidal linear looks like the following. We have B, we have elements A, and then we have three sets of lone pairs. The elements in the line go in the opposite direction, so they cancel each other out. The lone pairs make an equilateral triangle, so they cancel each other out. The octahedral looks like the following. The octahedral square planar looks like the following. We have B, and then we have A, lone pairs, lone pairs. The lone pairs here make a line, so they cancel each other out. The elements on the outside are in a square, and so they pull equally or push equally, so they cancel out. 2. Trigonal bipyramidal linear, octahedral square planar are the only two with lone pairs that will be nonpolar, as long as they are symmetrical. If they are not symmetrical, then they are polar. You did these problems in the previous slides. We're going to redo these using symmetry and lone pairs. Non-polar molecules have symmetry and no lone pairs, except trigonal bipyramidal linear and octahedral square planar. So this is tetrahedral bent. Since it has a lone pair, this is already polar. It is not symmetrical. Since it's bent, it is symmetrical vertically, but not horizontally if I cut it. CO2, if I look at my central atom, it is surrounded by two oxygens, which are symmetrical. So the outside is symmetrical. The central atom has no lone pairs. Therefore, this is nonpolar. CO3, we're going to look at the central atom. It is symmetrical. All the surrounding atoms are oxygen. and there's no lone pairs around C, so this is also nonpolar. If I look at NH3, it has a lone pair around the central atom, so this one is polar. The H's are the same element. Because of the lone pair, it is polar. CH3F, it's not symmetrical, so this is already polar. It has 3 hydrogens, but it has a fluorine, so it's not symmetrical. SCH4 is symmetrical. All the outside atoms are the same, and there's no lone pair, so this is nonpolar. BRF2 minus is symmetrical because it has fluorine on the outsides. They're the same element. Since it has lone pairs, it should be polar, but this structure is nonpolar. This is one of the exceptions. This is trigonobipyramidal linear geometry. So the fluorines make a line and they cancel each other out. The 3 lone pairs form an equilateral triangle and they repel equally. So they cancel their repulsion out. In IF5, this is polar because the central atom has a lone pair. The last one is nonpolar, even though it's symmetrical outside because all of the fluorines are the same. It has lone pairs, so you would think it is polar, but this is also an exception to the rule. This is octahedral square planar. The lone pairs are on opposite sides, so they cancel each other out. The fluorines make a square and they cancel each other out. So you can look for symmetry, so the same element on the outside of the central atom, and you can look for lone pairs. If lone pairs are present, then you already know it's going to be polar, with the 2 exceptions, which is trigonobipyramidal linear and octahedral square planar. So polar versus nonpolar. Polar molecules have a net dipole moment. Nonpolar molecules have no dipole moment. Individuals may be polar and nonpolar, and the overall molecule can be polar or nonpolar. And remember, likes dissolves likes. Anything that's hydrophilic, philic means to love, it loves water. Hydrophobics do not like water. And we know water is a polar molecule. If I draw the water molecule, it's tetrahedral, it is bent. Because it is bent, the overall polarity or the dipole moment goes towards the oxygen. The best way to determine the polarity of the molecule is 1. Draw the Lewis dot structure correctly. Look for symmetry. 3. Look for lone pairs. If it has symmetry and no lone pairs, then it is nonpolar, with the exception of trigonobipyramidal linear and octahedral square planar. If there is no symmetry, like water on the left, then it will always be polar. The reason water is not symmetrical is if I cut the water vertically, yes, it's symmetrical. However, if I cut it horizontally, it is not. Draw the Lewis dot structure correctly and look for symmetry and lone pairs.